Yeah, thank you. Thanks, Mario. It's the morning of long talk titles. You've had a lot of work to do in announcing these talks. Actually, as you're saying it too, you made me realize I should have flipped the order of the title, because I don't really actually have a lot of applications to composite materials here. The problems I'm going to talk about came to me from applied mathematicians who work in composite materials, and it took me a long time to realize what it is they do and what they're trying to do. But in the end, what I've kind of come to is that to really answer these questions, what would be useful is some spectral properties of the types of models we study here, so like random cluster models in statistical mechanics. And so the main purpose of this talk really is to try and interest all of you in working on some of these things and seeing if you can answer some of these questions and come up with new ways of analyzing these things. And yeah, the interaction here between probability and geometry that this is about, it's actually not very new. The stuff I'm going to say actually is about probably 50 years old. But I really think that the technology on the probability side has advanced to much farther than was intended when these things first came together, and could probably be used to go back and answer some questions about these mathematical methods behind composite materials. So like I said, these problems came to me from some applied mathematicians in my department. This is them here. And they basically study composite materials. So a composite material is just something that's made from two or more constituent materials with different properties. Okay? And I'll give some examples here in a second. But the main takeaway is that these different materials, they combine together at some microscale level. And at this micro, you can think atomic level if you want. And at that level, the behavior is very random. But then when you zoom out and look at these things at the macro scale in which we interact with them, then they behave as if they're homogeneous materials, essentially. And they have some effective parameters like conductivity, thermal conductivity, permittivity, things like this, that are a complicated function of the statistics of the small-scale random microstructure. Okay, so essentially these guys are they're homogenizers is what they're doing, and this is how they study composites. If you want to see more information about this stuff, the Wikipedia article on composite materials is pretty good. I also mentioned this podcast. This is an engineering professor at my university who runs this podcast on material science, lots of composite materials. It's actually pretty interesting if you really want to get into this. And I also learned it's very good for putting as broader impact on an NSF grant. So just to give some examples, a few examples of the type of composites they like to study. There's these polycrystals, which are just many small crystals fused together in some way. This is an example of them. They can have different shapes, different sizes, and then within each one, there's typically some orientation of like conductivity, or the fibers within the crystal might move in some specific direction, and they could be different in different crystals. And so often you want to understand for this type of material what is things like thermal conductivity, electrical conductivity. These things show up all the time. So for example, copper, even the copper wire that you buy at the hardware store is actually typically, it's not some pure thing, it's some polycrystalline thing. And the reason they do this is they mix it up with some other materials, is because apparently copper by itself is too soft, and it wouldn't be easy to work with without some extra hardness. So in dental implants, I was just telling Scott, there's this one that's called tetragonal zirconia polycrystals. Actually, this is a link. You can just go right to some website and buy this stuff if you want. Go and make your own dental implants. And then one that my colleagues like to study a lot is actually sea ice. They're very interested in using this composite material things to study melting of sea ice in the Arctic. And they often model sea ice as a polycrystal because it's made up of these little crystals of just frozen water, liquid brine, which doesn't freeze, and a whole bunch of air pockets. So, some examples. Another one, which is, just basically it's an example of percolation in action. These are these porous materials where it's just a two-phase composite of matter and something else. So lots of like rocks, solid soils, sandstones are modeled like this. Glacial ice, which is more pure than sea ice. Often this is just modeled as frozen water and a bunch of air pockets inside of it. And then bone. My colleagues have actually done a lot of work on modeling bone as a porous material. Apparently, I mean, if you zoom in on healthy bone, this is what it looks like. It's this, kind of gelatinous type material, but with all these holes in it. And then osteoporosis is just the process of when the healthy material degrades away and our bodies can't replace it fast enough. So the volume of air just increases. The volume of nothing increases. So. And then finally, the one which is probably the most commonly talked about in this context is these just conductors. So when you have some conductors, some metal made up of a whole bunch of different materials, and the conductiveness properties of these materials in some sort of percolation model determine the effective conductivity properties. So these things, again, show up in these cermets, ceramic and metal composites, polymer composites, and semiconductors are often modeled in this way also. So just some examples of the actual places these come from, but the mathematical models behind this, well, again, the idea behind it is always that these composites are just random mixtures of two or more phases. Each phase has some different physical property, but the goal is to understand the effective large-scale properties in terms of the statistics of this small-scale structure.
So why did you need AI to write this?
I was just impressed by it. I mean, it's in my editor now. Copilot's just sitting there and always suggesting stuff. And I typed in the title and it suggested the rest. And I thought, yeah, that's exactly what I wanted to say. So I'll just go with it. So let me give just an idea of a basic example of the type of models they use. Or one specific model they use and how they analyze it. What's the approach to homogenization that they use to extract out these effective parameters? So let's just work in R2, and we're going to have some random conductivity tensor at every point x in your, so x is your location in R2, omega is just indicating some random environment. If you want for this talk, you can just think of C as a 2x2 matrix that varies as you go through space. It's the diffusion coefficient of a Brownian motion, for example. But typically, this thing in the spatial direction will be rapidly oscillating. And then you want to solve some sort of, for each realization, you want to solve some sort of Poisson equation with some given collection of sources and sinks, and possibly some boundary conditions that make this well-defined, and depending on what situation you're in. But my colleagues actually like to study this not via solving for the potential phi, but for the corresponding fields, the electric field E and the current field J, which by Ohm's and Kirchhoff's laws just satisfy this system of equations. So current is just conductance times electric field. The divergence of the current is the sources and sinks, and this E should be a conservative field. So all these things will typically be rapidly oscillating at the level of the microstructure, which is what you would expect. But then to homogenize, the basic idea is always that you do some sort of transition from the micro scale to the macro scale, right? So you, at each point in space, you take an average of the random current field, for example, over some large box centered at that point. And then if you're in the setting where your random environment has some stationarity, ergodicity properties, you would expect this is roughly the same as the expected value of the current field over the random environment. And you do the same thing for the electric field, yes, and you compute an averaged version of that. And then the general belief of homogenization is that these two things, the average current and electric fields, satisfy the same system of equations, except the conductivity tensor is no longer random. It's replaced by some deterministic thing, which is, it's determined by the law of the random thing that you put in some very non-local and non-linear way. Okay. So any questions on that? Just trying to give a broad idea of how these homogenization ideas work. Okay. And typically, the fact that there is such a C star that, first averaging and then the averages will solve this equation, the fact that for some C star, the fact that you can do this is built upon some stationarity and ergodicity assumptions built into your random environment, plus some extra analysis, which is typically model specific. Okay. So once you have this idea, then there's, in fact, two types of homogenization problems. There's the forward problem and the inverse problem. So the forward problem is the most direct one. It's just computing this C star, which is non-random, from the law of your random conductivity tensor. And the problem with this is it's difficult to do in any sort of exact way, except in some very special integrable cases that come along every so often. The whatever functional it is that takes you from the law to the deterministic object is always very nonlinear and non-local. And whenever you can write down formulas for some sort of version of what this f is doing, it's typically given by some variational formula over an infinite dimensional space. I mean, we saw this for example, in the two talks this morning, where, for example, I'm most familiar with this in the context of last passage percolation, where these passage times, the limiting passage times, are some deterministic function of the law of the random passage times, but it's really not clear how to express that, one in terms of the other. There are known formulas in terms of variational formulas, but that's it. The inverse problem, though, is, if I give you the C star, then can you infer something about what the law of the random conductances was at the level of the microstructure? And that's something that, at least measuring C star is something you can do because it's it's an object that exists at the physical scale that we all work with, right? So you can do actual experiments on your composite material, get some estimate of this effective parameters, and then you want to go back from that and see what was the law of the underlying random microstructure, right? So the best example of that, my colleagues work on this a lot, is the osteoporosis example. You could think that the random microstructure is just some sort of version of a continuum percolation, right? With some parameter p. So with some parameter p at every point in space, you either have air or bone, right? And then you want to work out, you have a one parameter family of laws, this C star one parameter family of laws. This C star is also a function of that parameter. And then given the value of C star, go back and infer what the value of P was at the level of the microstructure. So, you can go and measure grandma's bones and based on the effective parameters, tell her, give her an idea of how much is actually left. So that's the idea. But to do this, for both the inverse or the forward problem, you have to have some understanding of, again, how you go from between these things, how you go specifically from the law of the random microstructure to the effective parameters back and forth. And so there is many ways to do this. Again, many of them come down to these variational formulas over infinite dimensional spaces. But I'm going to tell you about a method that my colleagues use a lot, which is they call the analytic continuation method. And so I'll try and explain this in a simple example and then tell you what we're trying to do with it. But before I go any further, I think in this audience specifically, I should make it clear that this actually has almost nothing to do with analytic continuation. So, the name it took me a long time to really understand that. So it's quite minimal. So again, this is the method that my colleagues really like to employ. It's based on some work that goes back to the early 80s by David Bergman, Graham Milton, Ken Golden here, and George Papanikolaou. It kind of came out right after these seminal Papanikolaou-Veridan papers on homogenization, and then it's kind of gone off in its own direction from that. And again, the main thing is it's a method for computing these effective parameters that doesn't rely on variational problems. Okay? But instead, what it relies on is a spectral decomposition of a certain random operator. And so here it's written chi gamma chi. Later you'll see it, I wrote it as 1 gamma 1. It's basically just a sort of a sub-operator of this gamma operator. And the gamma operator is an object that encodes deterministic geometry. This part encodes the random part of the geometry. So one of the advantages of this method is that it's sort of a perturbative thing, in the sense that if you have some actual material which is homogeneous, even on the level of the microstructure, in which you can presumably solve all these equations you want to, then you can do some random perturbations off that thing to understand the case of the random microstructure. And then from that, you can go and try and understand these effective parameters of the composite itself at the level of the microscale. Okay. So I'll try and say more about that, but the main, for these guys, the main reason they like it is because it gives them a nice way of computing these effective parameters via just lots of Monte Carlo simulation. So here's roughly how it works. Again, I think the viewpoint to take here is that you're going from a homogeneous version, a homogeneous material, to an inhomogeneous material. And you just want to see how various quantities change, like specifically in this case, how electric current changes under these perturbations. So if you have a homogeneous material, so just take the conductivity tensor as the identity, then you have a homogeneous current, a homogeneous electric field, and they satisfy this basic system of Ohm's and Kirchhoff's laws. Right? And the way they always solve for the current directly instead of for the potential. And they do that just by this very basic method of working with vector fields. They say gamma is the projection operator onto the space of gradient fields. And then with that, for any vector field on R2, you have the standard orthogonal decomposition into a gradient plus an orthogonal part. And of course, there's the whatever Helmholtz-Hodge decomposition that tells us the orthogonal part is just some divergence-free vector field. Okay. And so, of course, when we take the divergence of both sides of this part goes away, and you're left with the divergence of the original vector field is the same as the divergence of the gradient part. Right? So the idea is if you want to solve this equation for this current, this homogeneous current JH, then just find any vector field that has the same divergences that you want, and then just take out the part that's not a gradient. Right? So just project onto this basic gradients and get exactly what you want. So very simple idea. Nothing at all complicated about that. And then they just take this same idea and they do the same thing for the inhomogeneous case. So suppose you have some more general conductivity tensor. Now you have an inhomogeneous current, an inhomogeneous electric field, and you want to solve this system of equations with the conductivity tensor here can vary over space. Pretend it's just deterministic here even, don't even need the randomness. So you just introduce the same thing you want is that this current that you're trying to solve for should now be, instead of being strictly a gradient, it should be a gradient modified by this conductivity tensor. Right? So define gamma sub c is the projection operator into that space. Again, for any vector field on R2, you have this orthogonal decomposition into the, this part plus its orthogonal part. Again, the orthogonal part is just in the orthogonal space, obviously. But whereas in the last slide, what made this all work is the fact that the orthogonal space is just divergence-free functions. In this case, it won't be divergence-free anymore because, it's a different space here, right? It's no longer the gradients, it's this modified version of gradients. So, the trick is just very basic. You just change the inner product so that you get that so that this is true. So in a new inner product. And it's a pretty simple one. You just take, for two vector fields, this new inner product is just, you just take, it's just weighted by the resistances is all. I mean, it's very simple linear algebra. So in this inner product, yes, it will be, you will have that this orthogonal space is again the divergence-free vector fields. And so as a result, if you have any theta, well, when you take the divergence of both sides, the divergence of this will be the same as the divergence of this. This divergence will go away. Okay. So it gives you a way of solving for this inhomogeneous current just by applying this gamma C operator, the projection operator onto this range in this particular inner product. Okay. And this is why I want to emphasize it's a perturbative method, right? Gamma theta here, what the last slide said is that is the current in the homogeneous case, which presumably you can solve for that in some way. If you just apply this gamma C operator to it, then you get the current in the inhomogeneous case. Yeah, so knowing this gamma C lets you go from homogeneous currents to inhomogeneous currents. And that's kind of nice because, you know, even any small local perturbations in the structure of the conductivities C will lead to global changes in the way the current behaves. So this operator nicely encodes those global changes, right? So then the idea that my colleagues always use is that, okay, there is a formula that relates basically the current in the inhomogeneous case to the current in the homogeneous case via this operator gamma plus some submatrix of it. Okay. So in this case, the type of conductivity you're considering is just what's called a two-component thing. Okay, so on some set F, the conductivity is some 1 plus alpha, and off of F, the conductivity is just the identity. Okay, so it's just basically the diagonal changes depending on where you are. And then once you have, you can work it out. It's basically it's the ideas from the previous slide plus some linear algebra, which is, I mean, it took me a long time to understand how they do it, but in the end, it's not that complicated. You end up with this formula for the perturbations. Sorry. So again, what's nice is on the right-hand side just appears the homogeneous current, and then the key thing that appears over here is the what's called the spectral resolution of this operator. Okay. So this operator is just the gamma operator, but restricted to the subset F on which you have these different types of conductivities. All right. So again, it's pretty basic linear algebra. I'll explain it in a graph theory context in a second, but what's really nice about this is that if you believe in homogenization, if your F is random, then you don't actually care about this random current, this random inhomogeneous current. What you really care about is its expected value. Okay? So you just take expected value of both sides, where now the randomness all lives in this set F, which is where you're putting the inhomogeneous currents. And you just take expected value, and then everything passes through except into here. Okay. And since expected value, everything, these effective parameters can be entirely expressed in terms of expected value. From this quantity here, you can essentially work out what the effective parameters will be. All right. So that's the main idea. Let me just quickly say, I mean, the spectral resolution, that's a fancy word for simple object, right? Whenever you have some self-adjoint operator A, then mu sub A just basically encodes the eigenvectors and eigenvalues of A, right? If it's a matrix. So mu sub A is a matrix-valued measure or an operator-valued measure, however you want to think of it. But what it assigns to any interval on the real line is the projection onto the eigenspaces with eigenvalues in that interval. Okay. So it's just a fancy way of expressing this formula here ends up being a fancy way of expressing essentially the diagonalization of this operator, this gamma operator restricted to these subsets. Okay. So it comes down to a game of, again, just computing or understanding what is the spectral decomposition of this type of operator. All right. AI even could figure out that in this case, the eigenvalues will all be the spectrum's entirely between 0 and 1, simply because these two operators are both projections. So it's a simple fact, yeah, that the spectrum will be entirely in 0, 1 there. So any questions on the computation? Is very simple, very basic, mostly linear algebra. And the takeaway from it, though, is that for these random two-component types of conductivities, you can always express the effective fields and then essentially the effective parameters in terms of this quantity here, which is just some deterministic operator, some deterministic matrix. And since once you can express everything in terms of this, what my colleagues just do all the time is they simulate this by crazy via Monte Carlo, and then they use that for computing effective parameters, essentially. So they just make many, many realizations of this set F, diagonalize this matrix, compute, and then average out these random matrices over all these different realizations. Okay. So it's an interesting approach. And again, the key thing is no variational formula appears in there. Just averaging these random matrices, sorry. And just a few things to point out. So this only applies, as I've written it, when you have these sort of two-component conductivities, where it's basically one or two different values. That was just for simplicity. You can always express fairly general conductivities can be expressed as an iterative sequence of these two-component things. So in some sense, if you understand this, then you can understand everything else. And I only presented it also in the setting of electrical conductivity, but you can modify this approach sort of to do other physical quantities like permeativity, elasticity, just other settings for composite materials. Okay. And finally, I'll say, why do they actually call this thing analytic continuation? It's like I said, it's very minimal. It's basically because you have this alpha parameter, which was, I don't know, something like positive or something like this. This thing turns out to be, if you just look at this expression and work out where the cuts are of this thing, it's analytic off of the negative real axis. So I really don't know why they decided to call it this, but basically you can take alpha into the plane if you would like. So okay, that's a summary of how my colleagues do it. But it took me a long, long time to understand what they're even doing. I mean, we speak very different languages. So I had to take it back to something that I understand. And that's just basically discrete setting and electrical networks. And that's kind of what I want everyone else here to hopefully think about and tell me what you know about this stuff and hopefully make some contributions. And I think we can take the many things we know in the discrete setting and apply them in this framework. So why do I want to move to a discrete setting? Basically because the linear algebra is cleaner. It's much more transparent here. That was the main reason. What my colleagues are all doing anyways for these simulations, they're all based on graphs, so you might as well just understand what they're actually doing in the computer. You can, of course, nicely connect this to the statistical mechanics models that we study on graphs already. But the most important thing is that, so my colleagues are always doing averages of this random matrix or some modification of this random matrix. But what I came to realize is that they have no idea what they're actually averaging, basically. For any given realization of the this random set F in this case, they have no idea what this matrix should look like, no idea what any of its spectral properties actually would be, even though it's the key thing in everything else they do. So we really wanted to sink our teeth into that and understand how does this work just on a realization by realization basis. So the setup here is just an electrical network with some vertices, some edges, some conductivities on the edges. Again, you're trying to solve the Poisson equation, but you can elect to solve it instead in terms of the electric field E, which is just the gradient of the potential, and the current field, which is just the whatever by Ohm's law. And to do this, you just follow the same technique. And you introduce this matrix, this operator called gamma C, which is just projection operator onto this modified space of gradients in this modified inner product. Right? Not a complicated thing at all. And the way you solve for the current field J is you just find any vector field, any field on the edge set that has the right set of sources and sinks, and then just project out the non-gradient part of that. Right? Always the standard thing. And of course, this thing, once you see it here, I think it becomes a little easier to see that this thing has some nice probabilistic interpretations. My colleagues had no idea of any of this, so they were very impressed when I could just tell them anything about, probability relating to these things. So of course, this gamma is it's the covariance operator for not the GFF, but the gradient of the GFF, right? That's the one simple thing. The other is that, if you have the uniform spanning tree model, in which, a tree is selected at random on your graph according to these types of weights, just the product of the conductivities, then this is a determinantal process whose kernel is given by this gamma operator, right? This is this Burton-Pimentel theorem. And as Scott was saying in his talk on Monday, this is one of these just connections between Gaussian free fields and spanning trees that makes each one so useful for studying the other. Right? But again, to go back to what my colleagues were doing, the linear algebra for how the gamma works for one set of conductances with a different set of conductances is a lot easier in this graph setting case. This is, even just teasing this out in the setting of a graph made it much easier than working in their continuum versions. So here what this is you start with any set of conductances and then just do this sort of two-component perturbation of them. So on some edges, you multiply it by 1 plus alpha. On the other edges, you just keep the conductances the same. Okay. And then the gamma matrix for this modified set of conductances can be expressed entirely in terms of the gamma matrix for the original set of conductances, up to some, you need this particular submatrix of the original gamma matrix. Okay. And you just do this in a nice, basic linear algebra stuff, and then if you want to rewrite this back in terms of the spectral resolution of this operator, this submatrix, then the formula looks exactly like you see it it's presented in the continuum version. Okay. And in this setting, you see it's really simple, right? It's just, in this case, this formula is just an application of one of these Sherman, Morris, and Woodbury formulas for matrix inverses. You can also think of it as some version of a Hadamard variation formula. One thing that we were able to tease out that they hadn't seen before is that it only really matters that the perturbation is two-component. It doesn't matter that the original set of conductances is purely homogeneous. You can start with whatever you want. As long as the perturbation is of this two-component type, then the analysis all goes through. But if you're going to use their approach, again, what you need is to understand on a realization by realization basis, what is the spectral decomposition of this suboperator. And for the same reasons as in the continuum, the spectrum will be entirely within 0, 1. Again, it's easier to see here because this is also the kernel of some determinantal process. But what's interesting about this formula is you notice that this is open endpoints here. So in fact, for doing these perturbative things, you don't need to know the part of the spectrum at 0 or 1. Somehow it's already encoded in the thing that you started with. Okay. So then we started looking, and even just finding some of the basic spectral properties of this suboperator turned out to be, they're not really hard, but we didn't really see them anywhere. And so, for example, if you want to, the spectrum of this thing naturally breaks into these 3 pieces: the part at 0, the part at 1, and then the part in between. And the parts at 0 and 1 are basically trivial. But the part in between 0 and 1, which is actually where all the important stuff is for this perturbative formula, that they didn't really know anything about. So just some basic graph theory type ideas. We were able to do things like count, okay, how many eigenvalues should they expect in this middle part, in this part between 0 and 1. And that's just a basic quantity that can be expressed entirely in terms of connected components of subgraph counts. So that's what these things are. You have your set of vertices V with this subset of edges F, and then the complementary subgraph. Just by counting the connected components of those 2 things, you can get a handle on how many eigenvalues appear in each of these. Okay. And then we give some description of what the eigenvectors should look like in these different settings. We express the ones in the middle here as solutions to some generalized eigenvector problem. Not strictly an eigenvector problem, but a generalized eigenvector problem. And even just taking some of these results and modifying their Monte Carlo code for computing this expected matrix, this sped it up actually quite a bit. So they were just doing very naive things for that. So that was one thing we were able to tell them. Li-Fu Chen, who's here, and he pointed out to me this very, it's really just a property of determinantal point processes, but it's a characterization of this part of the spectrum. It just says that the characteristic polynomial of this suboperator can be expressed entirely in terms of as an expectation over spanning trees. So T here is just the uniform spanning tree, and that's what you're taking the expectation over. A former student of mine, Lauren, she took the spectral statistics that were on the 2 slides ago about the eigenvalue counts in these different ranges, and she worked out how it changes when you have Dirichlet boundary conditions instead of the ones we were doing before were actually like some sort of mean 0 boundary condition for the potential. So she worked out, in the presence of Dirichlet boundary conditions, how do these things all change? Not very complicated formulas again, but just by basically counting clusters. That's all it comes down to. Another student, well, here she is. This is Han Lei. She's now a postdoc in Waterloo. But she did a nice little computation when the spanning tree, so when this random subset F actually is just a spanning tree. So when I do this 2-component thing, but where I put the modified component is on some spanning tree, she worked out this way of computing the part of the spectrum in 0, 1 for, this is like 1 sub t, gamma 1 sub t. Basically what she said is that if you have your spanning tree, you look at the edges that aren't on the spanning tree. Sorry, these guys here. And then, of course, to each one there corresponds some cycle in that spanning tree. you just compute this overlap between different cycles, weighted by the resistances. This is some Gram matrix, and the eigenvalues of this end up turning into the eigenvalues of this in this form. So if lambda is an eigenvalue of this guy, then 1 over 1 plus lambda is an eigenvalue of this guy. Okay. I mean, this was just a nice example, I think Scott mentioned in his talk, of how lots of times by computing sort of these intersections of spanning trees, you can understand lots of properties of these systems, and this is how it works in the case of these spectral statistics, or one example of how it works in spectral statistics. And the argument she gave for this is very simple, right? It's just that you're trying to find this gamma is a projection onto some range of gradient operators, or it's a space of gradients. Every spanning tree on a graph gives a natural basis of these gradients. And if you just compute the gamma matrix via the spanning tree that you're working with, then this cycle overlap thing appears. And that's how the analysis goes. Another place we've been trying to, we'd actually like to really compute some of these actual effective parameters in some setting. A sort of toy model we've been working with is these random iterated function systems. So here's an example of this. You just choose your favorite probability measure on positive reals, and then take sample 4 IID random variables from that thing, and then form a new random variable just by this rational function in those 4 things. Take the law of that thing, call it, say, mu1, and then just iterate this over and over and over again. Okay. So yeah, random iterated function system. And the question is, does some sort of limit of these probability measures exist as j goes to infinity? And if so, how does it depend on the initial choice of measures? And of course, this particular, particular form of this rational function that I chose, there's a reason for it. It was just some sort of recursive structure that we could come up with. That thing is just the effective resistance on this diamond hierarchical lattice. So the sequence of lattices where you start with one bond connecting 2 vertices, and then you just iteratively replace every bond with this diamond thing, and keep going further and further out. And of course, so the mu j will just be the law of the effective resistance on diamond j when the resistances or the conductances maybe on each edge are chosen according to mu naught. So there's an extensive literature on the existence of a limit for this type of scheme with very minimal assumptions on the properties of mu naught. But what's still not, I don't know of many cases where the dependence of the limiting constant, I should say the limit is always a delta mass at some constant. The randomness will always disappear. The effective resistance in the end will always be just a constant. But how that constant depends on the initial choice of resistances is still poorly understood. So my former student Lauren, in this case, she was able to say, when you have this, just this 2-component thing where with probability p, your resistances are h, with probability 1 minus p, they're 1. Okay, she could give an expansion of this thing, a perturbative expansion of this thing in powers of h around just h equals 1, which is the homogeneous case. And it's all based on just an analysis of this gamma matrix and the submatrices and so on. Okay. Well, that's another student working on some modifications of that, but I think I'll just end here with saying, what are some of the things I'd like to do with this, or I'd like some input on to see, if any of this can go further. So a lot of it comes down to, computing the spectral properties of these random operators. That's the main idea behind this particular homogenization technique. And this operator encodes somehow both the deterministic geometry that you're working on in the background, plus some random perturbation of it. And I think and there's no nice way to compute these eigenvalues or eigenvectors, but it would be nice to be able to at least express them in some probabilistic way. More general probabilistic ways that are amenable to taking infinite volume limits or scaling limits or things like this. The other one I'd like to really understand is, so it's this perturbative approach where you're just constantly changing the geometry little by little, which is one of the main ideas that makes things like SLE work, right? A big thing we learned in this business is that you should explore these random bits little by little. Right? So how would that, if you were to couple that with just changes in spectral properties, how would that work? Another thing I'd like is, so with the two talks this morning, we saw about these nice, how often these surfaces or these maps can be expressed through these, like Hamburger-Cheeseburger bijections and various relations with random walks. I would be very interested to see if any of these spectral properties of the map can also be encoded in terms of these random walks. For one thing, the simple eigenvalue counts that I presented a few slides ago, it's already clear that those things are easily encoded via the random walks. But it would be nicer if there was more detailed information about the spectral properties.
But what spectral properties besides eigenvalues?
I mean, eigenvectors also is kind of, you need the whole thing for this really to work. So, yeah. Yeah. So, and I'll jump to the last one here. So, actually, when my colleagues came to me with these problems, they didn't care about me going in and trying to understand what they were doing. What they really wanted is they're doing all these simulations to compute, estimate expected values of this random matrix. But within all these simulations, they start doing some analysis of the random spectrum that they see. And then they start to, they claim that they see connections to like GUE, GOE. The Wigner surmise is the one that they most frequently pick out. It's about spacings of eigenvalues in under some sort of scaling. We've made no progress on that, but you look at their graphs and it kind of seems sort of convincing. I'm not entirely sure I trust their numerics fully, but it seems like there could be something there. So that's another thing I wanted to say. It's just something that I hope that in the future, someone will come up with some ideas about these things. So thank you.